Hey guys, Mr. B here, and in this video we're going to be going over the Chapter 2 review guide. This is a PDF that I've opened up, and I'm using an extension for my Google Chrome browser called Cami. If you go to the Google Chrome store, you can just add this extension onto your Chrome browser, and it just lets you type and edit PDF files. So this is a PDF. You'll have a Google Doc version, but if for some reason you had a PDF version, you can use Cami to edit it. So anyway, let's just get started. So here we go. Number one, describe the difference between an extensive property and an intensive property and give an example of each. So remember, the extensive properties are dependent on the amount of matter you have in a sample, and intensive properties are dependent on the type of matter you have in a sample. So we're going to write that down real quick, and then we'll go over some examples. So extensive depends on the amount of matter you have. Intensive, there we go, depends on the type of matter you have. And then for examples, we'll just go e.g. e.g. is a shorthand for just saying like example. So example, so for extensive would be like mass. And e.g. again, e.g. is just shorthand for example. So for example, that's what e.g. stands for if you didn't know that. Intensive property could be something like boiling point. Okay. All right. Number two, name two physical properties that could be used to distinguish between water and ethanol. So water, obviously most of you know what water is, but ethanol is drinking alcohol. Same alcohol that's found in any alcoholic drink that you could ever think of. Okay, it's the only alcohol that we humans can actually drink, and it won't kill us. So, or at least not in small amounts. So, name two physical properties that could be used to distinguish between water and ethanol. So, if you had a bottle of water and a bottle of alcohol, they're both clear liquids. Just by looking at them, you probably couldn't tell the difference. But there are ways, of course, to distinguish between them too. So if you've ever smelled alcohol before, and I'm sure your parents have been around and had alcohol open, hopefully, obviously you haven't drank any, but if you ever smell alcohol, it has a pretty distinct odor to it, right? It smells pretty strong. So one physical property we could use would be odor. So if it has a distinctive odor to it, water doesn't have an odor, or at least typically it doesn't. We're not talking about like tap water or something. Just plain, distilled water that would come in a bottle doesn't smell like anything. So whereas alcohol does. Another physical property that we could use would be boiling point. So if you've ever cooked with alcohol before, or if you've ever seen your parents do it, or there's like cooking wines. Alcohol boils off at a pretty low temperature. It's pretty easy to get it to boil on your stovetop in like a pan or something. Water has a higher boiling point. So alcohol will boil off first, water will boil off second. So boiling point's another one we could use. You could say a second property would be boiling point. That is also a physical property because, again, if you were to boil water, it would just become a gas, but you could condense it back to liquid. And if you were to boil alcohol, it would become a gas, and then you could just condense it back down to a liquid. So, you're not changing what the material is, therefore it's a physical property. So, there's lots and lots of other physical properties. You could use density. You could use I'm blanking right now. Density, I guess you could use freezing point. That'd be another one you could do. There's a few different ones. So, all right, number three. What is the physical state of the following materials at room temperature? So remember the three physical states are solid, liquid, gas. Pretty simple one. I'm going to leave most of these ones for you to do, I guess. Neon, by the way, is a gas. So that's the only one that I'll do because like neon signs, like if you go to a restaurant or a bar and they have signs that say open or, whatever, those are gases that are running through the tubes. So neon is a gas. So if you didn't know what neon is, that's one. And mercury, I'll do that one too. Mercury is a liquid. It's one of the only metals that's a liquid at room temperature. Most metals, of course, are solids. So the rest of those ones, I think you guys can do probably just fine on your own. So Number 4, compare the arrangements of individual particles in solids, liquids, and gases. Okay, so this one comes from the notes where it basically is asking what are the particles like in a solid versus a liquid versus a gas. So to remind ourselves, in solids, the particles are very tightly packed together. Okay, they can't go anywhere, so they're like locked in place. That's what makes solids solids. That's why they stay and keep the same shape and they have a defined volume. So we can say that the particles are tightly bound together and can't move. Okay. In liquids, the particles are still connected to each other, but they're much loosely connected, so they can kind of slide past one another, move past one another. That's what gives liquids the fluidity that you're used to thinking of when you think of a liquid. So you can say the particles are more loosely grouped together and can move past one another. And then as for gases, I guess we'll just put this one somewhere like over here. There we go. As for gases, the particles are pretty much just completely individual on their own. They're not connected really in any way. They're very, very loosely connected, but not really. So they're pretty much just individual particles. And, you know, if they're trapped in a container, they'll be next to each other. But as soon as you open that container up, they just go wherever they want. So gases will say the particles are individual particles, something like that. So they just kind of go all over the place. All right, number 5, explain why sharpening a pencil is a different type of physical change than freezing water to make ice cubes. So remember that when it comes to physical changes, there were 2 types. Okay, there's reversible physical changes and irreversible. So the difference between sharpening a pencil compared to freezing water is that sharpening a pencil is irreversible. Once you've sharpened that pencil, you can't take the pieces that you sharpened or, you know, cut off of it and put them back on. Whereas freezing water is reversible. So you can freeze it, then you can melt it, then you can freeze it, you can melt it, and go back and forth and back and forth and back and forth. So we can say the difference between the two is that sharpening a pencil is I'll even capitalize it, irreversible, and freezing water is reversible. Okay, there we go. Number 6, what is the difference between a homogeneous mixture and heterogeneous mixture? Okay, so homogeneous mixtures are mixtures that have one phase, or basically that look the same throughout them. Okay, so they have a uniform look. And heterogeneous mixtures have 2 or more phases, or basically they have multiple parts to them that you can see with your eyes. Like you can see the different pieces, okay? So we're going to use our proper terminology here. So we'll say that homogeneous mixtures have only one phase. And we'll say heterogeneous mixtures have 2 or more phases. Okay. And you'll notice that I capitalize words on purpose just to make sure that we really, like, those are the words that really distinguish what we're talking about, right? So one of them has one phase. We really want to make sure people understand one phase. The other one has 2 or more phases. All right, number 7, how many phases does a solution have? So number 7 is pretty much like number 6, only they're using the word solution, which, to remind ourselves, solution is just another word for saying a homogeneous mixture. So we basically have already answered this question. So we can say that a solution has one phase because it is a homogeneous mixture. Okay, so we basically already answered that with question 6. All right, number 8, classify each of the following as a homogeneous or heterogeneous mixture. These ones I'm going to let you guys do on your own. You know, try not to like overthink them. Okay, so if you really aren't sure, you can always email me about them or ask, but I think you can probably answer those ones just fine on your own. Number 9, what is the goal of a distillation? Briefly describe how this goal is accomplished. Okay, so distillation was one of the ways that we can physically separate out liquids from each other. And as to how that works, it works by first we boil the liquid and it will turn into a gas. And the liquids, of course, will boil at different temperatures. So they'll boil and turn into gases at different rates. And then we run those gases through a distillation column, which basically is a tube with an outer tube going around it in cold water. So the liquids will boil into a gas, go up the tube. They'll go down the distillation tube, they'll cool down and condense back to a liquid, and then we can collect them in a jar or a container over here. And because each liquid boils at a different temperature, like one will boil first and turn into a gas and then condense, we can collect it. Then the next one will boil later, which then it will, condense, and then we can collect it, and just keep on doing that until all of them have been separated. So basically, we'll say the goal of a distillation is to separate out liquids from each other. There we go. I'm going to need a space. And this is accomplished by boiling the liquids into gases and then condensing them back down into liquids. Okay, so, all right. Number 10, how could you distinguish between an element from a compound? So remember that the difference between an element and a compound is that compounds are basically made of two or more elements that are chemically bonded together, whereas an element obviously is just by itself. So as to how we can distinguish between the two, compounds can be broken down into simpler substances. Elements cannot. Okay, so we can say that to distinguish between an element and a compound, compounds can be chemically broken down into simpler substances, while elements cannot be. Okay, something like that. All right, number 11, describe the relationship between the three items in each of the following groups. Identify each item as an element, compound, or mixture. Okay, so what we're going to do is just basically describe how these three things are related, and then, is each one an element, compound, or mixture. So hydrogen, oxygen, water. So the relationship for this is that hydrogen and oxygen chemically combine to make water. Okay, so we'll say that hydrogen and oxygen chemically combine to make water. And then identify each one as an element, compound, mixture. So we'll put a little text box up here. So hydrogen is an element. Oxygen is an element, and water is a compound. Move it over a little bit. Okay, so there you go. So element, compound. Okay, nitrogen, oxygen, and air. So the relationship between these is that the air is primarily 80% oxygen and about 20%. The air is about 80% nitrogen and about 20% oxygen. So the relationship is that nitrogen and oxygen both are mixed together to make up most of air. And then air itself, of course, is a mixture. So we will say that nitrogen and oxygen mix together to make up most of the air. And then as for each one, we have a little bit of space, so I'll just kind of write it above. So nitrogen will write E for element, oxygen will write E for element, and air we will write capital M for mixture. Okay, because it is a mixture. All right, sodium, chlorine, and table salt. The relationship between these three is that sodium and chlorine both chemically combine to make table salt. Okay, so we'll say that sodium and chlorine both chemically combine to make table salts. Sodium and chlorine are both elements, and table salt is a compound. Okay, so sodium is an element, so write capital E for element. Chlorine is an element as well, so write capital E for element. And table salt is a compound, so write capital C for compound. All right, carbon, water, and table sugar. Carbon and water both chemically combine to make table sugar, and table sugar therefore is a compound. So we'll say that carbon and water both chemically combine to make table sugar. And carbon is an element. Okay, water is a compound. We know it's a compound because we actually answered that one up here in letter A. So we know it's a compound made out of two elements, hydrogen and oxygen. And table sugar is just a more complicated compound. So table sugar is actually a compound made out of another compound plus an element. Okay, number 12, name the elements found in each of the following compounds. So we just have to name the elements. You'll need a periodic table to do this. You can either go Google one. There's plenty online. So ammonia is the name of the compound, but the elements in here are N and H. So N would be nitrogen and H would be hydrogen. Okay, so the elements that are in the compound are nitrogen and hydrogen. That's all we're doing. Okay, the numbers and everything else don't really matter. So we'll take a look here at letter C, and then I'll let you do letter B and letter D because this one isn't that hard of a question. So letter C, sucrose, which is C12H22O11. We have C, which is carbon, H, which is hydrogen, and O, which is oxygen. Okay, so we're just naming the elements. That's it. Again, all you need is a periodic table. If you have any problems, though, with that one, just email me and I will help you out. All right, number 13, what does the formula H2O tell you about the composition of water? So H2O, the chemical formula, tells you what elements are in the compound and how many elements of each are in the compound. Okay, so it tells us that the two elements in the compound are hydrogen and oxygen, and it tells us that there are 2 hydrogens and 1 oxygen in the compound. So we can say the formula H, and I don't know how to do the little numbers. So H2O tells us the types of elements in the compound and how many of each element are in the compound. Okay, so chemical formulas always tell you the types of elements you have and how many of each one. Okay, last section here, number 14. Use the word equation to explain how a chemical change differs from a physical change. So they have here iron and sulfur, and you heat them up and you get iron sulfide. So the main thing that really we need to see here and what we need to understand is that a chemical change differs from a physical change in the fact that you are starting with some kind of material or materials, and you're ending with completely different materials. Okay, so the main difference is that in a chemical change, you're starting with one stuff and you're ending with a whole new material. Okay, so you're making something new. So we can say here that we'll say using the word equation, we can see that this is a chemical change because the starting materials, and we'll say reactants, okay, to use our proper vocabulary here, because the starting materials, reactants, are different from the ending materials, products. Okay, and then we'll just to finish up, we'll say in a physical change, the reactants and products would be the same, right? So basically it's just saying that using this word equation, we can see that this is a chemical change because the starting materials, the reactants, are different from the ending materials, the products. In a physical change, the things you start with and end with would be the same because you're not making anything new, okay? And in this problem, we are obviously making something new. Okay, number 15, classify each of the following as a physical or chemical change, and for any chemical change, list at least one clue to support your answer. Okay, so letter A, a copper wire is bent. This would be a physical change because we're not making any new material. The copper is still copper, even if it's bent or straight, still copper. Okay, so we'll just say physical change. We only have to put a clue if it's a chemical change. Okay, and this one is not. Letter B, charcoal burns in a grill. Okay, so this one is going to be a chemical change, and one clue that we could give to show that it's a chemical change is a transfer of energy. When you burn charcoal, it gives off heat, right? Which it means it's releasing energy, and that's one of the key indicators that a chemical change is taking place. So we can say chemical change, one clue is that there is energy being given off in the form of heat. Okay. All right. Letter C, bread dough rises when yeast is added. So bread dough rises because when you add yeast to dough, it eats sugar and it creates carbon dioxide gas. And as the carbon dioxide gas is formed, it tries to escape and it expands. Of course, the bread dough is very sticky and it's like a net. So it traps the gases in there, and the bread dough essentially expands as the gases try to escape. And eventually, of course, the dough will break and the gas will make its way to the surface and it will get out. So if you ever look at a piece of bread, there's usually holes on the top. And if you cut open a piece of bread, you'll see all these little holes in the bread itself, and those are all little gas pockets that formed when the carbon dioxide gas formed during the baking process, but eventually was able to squeeze its way out of the dough. Okay, so this is a chemical change. And we'll say one clue is that a gas is being produced which causes the bread to rise. Okay, so it's the formation of a gas that causes the bread to rise. That's the clue. All right, letter D, sugar dissolves in water. This one is a physical change, and we know that this is oh my gosh, I can't type. Physical change. There we go. We know that this one is physical change because if you dissolve sugar in water and you drink the water, you can still taste the sugar. So you know the sugar is still there. It hasn't turned in anything new. Okay, so it's going to be physical. And we don't have to give a clue for this one because it is not a chemical change. All right, number 16, which type of property cannot be observed without changing the composition of a substance? So for number 16, the type of property they're talking about here are chemical properties. Okay, the only way to observe a chemical property is to actually change the composition of a substance by doing something to it, right? So let's say, for example, we wanted to test the chemical property of flammability, which means can you light it on fire? If it does light on fire, that material is now going to be something completely different from before we lit it on fire. Okay, so the only type of property that cannot be observed without changing the composition would be a chemical property. So we'll say the type of property that cannot be observed without changing the composition of a substance is a chemical property. Okay, because physical properties can be observed without changing the composition. Okay, that's how they work. So, all right, last one here, number 17. When ammonium nitrate, whatever that is, and they give us a chemical formula for it, explodes, the products are nitrogen, oxygen, and water. When 40 grams of ammonium nitrate explode, 14 grams of nitrogen and 8 grams of oxygen form. How many grams of water form? Okay, so this is a law of conservation of mass problem. So here's what we're going to do first. I'm just going to write out an equation to kind of show what's happening, okay? So we have ammonium nitrate, which explodes, and it says the products are, okay? So this is a reactant. So ammonium nitrate explodes, and we're going to make nitrogen, oxygen, and water. Okay, so this is just showing us here's what we're starting with, here's what we're ending with. Then they tell us that if we have 40 grams of this ammonium nitrate, okay, so 40 grams of this ammonium nitrate, we get 14 grams of nitrogen plus 8 grams of oxygen plus some number of grams of water, okay? And the question is, how many grams of water will we make? This is just a basic subtraction problem. Remember that the law of conservation of mass says the total amount of stuff you start with has to be equal to the total amount of stuff you end with. So if we're starting with 40 grams of ammonium nitrate, we need to have 40 total grams of product at the end. So we'll say the law of conservation of mass says that the total mass you start with must equal the total mass that you end with. Okay, so basically all we're going to do is we're going to add up 14 plus 8 and then take 40 and subtract it, and whatever the difference is, that's how many grams of water we're going to make. Okay, so we'll say 14 grams plus 8 grams equals, this I believe is 22 grams. Okay, so that we have 22 grams of stuff on the right so far. Okay. And then, of course, we have plus question mark. And then all we're going to do is we're going to take 40 grams minus 22 grams equals, and that will tell us how many grams of water we can make, or how many grams of water we make. So I believe this is 18 grams of water form. Okay, and we'll underline this. There we go. We'll underline it just so we know that's our answer. Okay, so we will make a total of 18 grams of water. All right, that is the last question. Hopefully that helped you. If you have any more confusion though for this chapter, just reach out to me. I have no problem sitting down with you and doing some personal one-on-one tutoring if you really need it. Okay, or talk to me in class. So, all right, guys, that's it. I'm Mr. B. Good luck with your test. See you in the next video. Bye.